Good luck. Yeah, it's the sun god. It's Huitzilopochtli. It's a Aztecan sun god, and this is Apollo, the Greek sun god. So in all cultures across the world and across time, the sun has been the prominent deity, if not a prominent deity, as the giver of life. And now, it's the energy and climate crisis. I think the sun will be our savior once again. No coal god. Yeah, I know. What's the deal with that? Um, and then yeah, this quote by Thomas Edison kind of cracks me up, um, in a gallows humor sort of way. I sure hope we don't have to wait until oil and coal run out before we use solar energy. All right. So we've seen this bar chart before. And it's a horrible bar chart. You have a logarithmic bar chart. The whole point of bar chart is to see uh, size relations between numbers. And so when something's twice as tall, it should be twice as big. But as soon as you have this logarithmic axis, then twice as tall means nothing at all, really. But it's plotted logarithmically just because these numbers vary so significantly. And so this is the exergy flows of power. So it's a power flow available to planet Earth. Human use of energy is about 15 terawatts. So if you plugged in all of society, it's somewhere between 15 and 18 terawatts. And that's the scale of one here. And so with solar energy, there's nearly 10,000 times more energy, more power than all of society uses available to us. And so it shows the most promise. We can run society 10,000 times over just on solar energy alone. Wind energy, which is actually just this form of solar energy, the sun heats up the atmosphere and creates wind currents. We have about 10 to 100 times more power available to us than all of society. So there's tremendous potential in both solar and wind for satisfying society's power demands. The trick is they're intermittent, they're weather dependent, and you can't store them very easily yet. We're getting better and better at that every passing day, but it's nothing like coal or oil where you can just stack it up in a big pile or put it in a big tank. So that's the real trick, transitioning from these stores of energy, oil and coal, to natural flows of energy, wind and solar. Here's net electricity generation in the United States over the last 20 years, so your lifetime. And I'm colorblind, so I'll have to kind of geek my way through this. This is coal, and it's been falling with the advent of horizontal drilling and fracking as natural gas has replaced coal largely, but not quite all the way. The rest of the replacement has been done by wind and solar. And so here's wind, and I'm guessing is brown, maybe green, and here's solar in blue down here, growing up. Yeah, so somebody's asking about these peaks and why are the peaks close together? Let's go to the next chart to see if we can't figure out that question. So this is zooming in on just the last 5 years. And let's look at solar. It has a peak and then a valley, and a peak and a valley, peak and a valley. And the valley happens right at the new year. Yeah, seasons. So it's obvious what's going on with solar. The sun shines in the summer, at least in the northwest and the whole northern hemisphere for that matter, and then far less sunshine in the winter. And so that's what's going on with solar. But the same thing, going back to the last slide, occurs with coal and natural gas. It's not that there's more natural gas or more coal in the summer or winter. It's just we burn a lot more coal and gas in the winter to stay warm. Somebody in the chat, Melvin asked, where's this data collected from? This is all from the Energy Information Agency.gov. Your tax dollars pay for this. And this electricity data browser is really clever. You just pick the years and what you want to plot against one another. And so I generated these plots this morning. Where's the data actually collected? It's part of the Federal Electricity Regulation Committee or something, FERC. I don't know what the C stands for. They require all power providers to say how much power they generated over the course of each year. I actually think they have to report every month. And so Yeah, the federal government collects this data and then distributes it via this EIA portal on the web. And this data is just for United States. It gets trickier with other countries, as you all experienced when you tried to get data for Mauritania. All right, so zooming in on just the last 5 years and only renewable resources, you can see that we're dominated by conventional hydroelectric, and wind is growing and is now at parity with conventional hydroelectric. Solar trails behind in capacity, but it's growing as well. Geothermal has remained relatively constant throughout that time. There's a few really great locations like Geyserville, California, that have been tapped, but other places are not economically viable, so it hasn't taken off like wind and solar has. Why has wind and solar taken off? It's because they've become economically competitive with with coal and gas. And so this chart shows the levelized cost of electricity, which is a pretty wonky idea that I won't spend time going into in this class. But if you take some of the econ professors' classes in energy, like Reed or Sharon, they go into this quite detail. But it tries to estimate how much it costs to deliver a megawatt hour of electricity from one of these sources, counting the cost of the fuel, the cost of building the plant, all those different capital and operating and maintenance costs that may be involved in fuel cycle costs. So here is utility scale. So if Puget Sound Energy or SoCal Edison or something like that, a big utility bought a bunch of solar panels, this is their levelized cost of electricity to generate a megawatt hour. It's $46, or that's also in terms of what you may be used to kilowatt hours, that'd be 4.5 cents per kilowatt hour. And so you can see that this is now at parity, if not cheaper, than a combined cycle natural gas power plant, and far cheaper than a peaking turbine gas power plant. It's cheaper than coal now, and far cheaper than things like nuclear power. And so solar at utility scale is the cheapest form of more available power. Wind is also quite cheap too, but it can get more expensive depending on the location on where it's installed. Yeah, so Jonah wrote in the chat, so is this saying a solar panel on a residential roof is more costly? Yes, that's just due to economies of scale. If you have a big field out in Eastern Washington, that's flat, you can just put in a tremendous amount of panels for a lower cost. Whereas, I have 16 panels on my roof that required a permit, a crew, and they only put in, 5 kilowatts of capacity. And so it's just economies of scale. If you do things big, you get a discount. It's buying in bulk, right? That's basically what it is. Tony wrote in the chat, efficiency as well, tilt scale, ideally sited. So yeah, when you build a utility scale installation, you'll get more power per unit panel because the panels will be ideally sited. They don't have to conform to the architecture of a roof. Point of this plot is that wind and solar are cheaper than gas now. If not, they're at parity, if not cheaper. Why is this happening? It's because it's getting cheaper and cheaper to build wind and solar as we learn as we build more of them. The economies of scale and learning by doing. I brought this up last lecture, that the whole idea that if you build a picnic table, it may take you all weekend, but the second picnic table will just take you a day, and the third picnic table you build will only take you 4 hours. It's just, you'll get used to making the cuts, learning where the screws go, all that sort of thing. Same thing is happening with renewable resources, wind turbine generation, and solar panel manufacturing. A study back in the 70s, NASA determined that any new technology, for every doubling of production, for every time you make twice as many as you had before, costs go down by 20%. Now, that's not a rule of nature, but that seems to be this empirical law that's present in our economy. And this also means that solar panels and wind turbines will still have room to get cheaper and cheaper and cheaper because we're very early on these learning curves. We haven't built a ton of them yet. This is certainly the case when you compare it to something like a natural gas turbine or coal or an automobile or something. Those have been pretty tapped out. I mean, now we're doing this paradigm shift from gasoline powered to electric vehicles, and so now we get to hop on a new learning curve. And you can see that with the price of electric cars and battery packs going down precipitously over the last 10 years. And so wind and solar, it's cheaper, if not as cheap as gas right now, and it's only going to get cheaper. The other great thing about renewable resources, and the greatest thing, is that they don't produce much carbon. They don't produce any carbon when you're operating them. They don't smoke. There's no smokestack on them. There is a little bit of carbon associated with their manufacture, right? When we talked about life cycle assessment on the fourth lecture. And so the National Renewable Energy Laboratory in Boulder, Colorado did these life cycle assessment studies earlier this decade. And they found that on average, manufacturing a solar panel will produce, over the course of its life, 39 to 49 kilograms of CO2 per megawatt hour of electricity it generates. And the CO2 is all associated with the upstream. And that makes sense. It's associated with manufacturing the thing, melting the silicon, cooling it down, putting the laminate on the glass, the conductors, gluing it all together and shipping it. Once it's put up there, there's a little bit of CO2 associated with maintaining it. You have to clean off the bird crap once a year, right? Blow the leaves off the solar panel, the dust. And so there's a little bit of CO2 associated with maintaining them. Wind, again, it's all in the upstream, building the wind turbine itself, the carbon fiber blades, but it has the lowest CO2 of the three that I'll show here. Hydropower can get lower just because these dams can last for like 100 years. But wind is 3 to 45 kilograms of CO2 per megawatt hour. Again, all associated with the upstream. We can compare this to natural gas, which is about 500 kilograms per megawatt hour. And so we have this factor of 10 less CO2 per megawatt hour from these renewable resources than natural gas. So don't let pundits or people trick you and say that, oh, well, solar panels are environmentally damaging too because all the CO2 that's emitted when you manufacture them. Yes, the CO2 is emitted, but it's pales in comparison over the life cycle of these two different technologies, gas versus solar panel. And I recalled Friday when I was talking about when I heard somebody on that Joe Rogan podcast, which I'm not a big fan of, say that that electric cars are just as bad as gas cars because they're powered by coal. The idiot that was saying that was Alex Jones. So I think I know I just made a ad hominem attack, and that's the logical fallacy, but I think most things he says might not be exactly right. All right, so the CO2, of course, with gas turbines, all associated with the fuel cycle. You're lighting carbon on fire, it's going to make CO2. Okay, I'm going to get a little US centric here and look at where wind energy works best. So this is average annual wind speed at 30 meters in, have not watched Michael Moore's Planet of the Humans, so I'll have to check that out. So here is annual average, but I did hear some drama about that. Anyways, I'm gonna get distracted. Annual average wind speed at 30 meters above the ground, and it's strongest in these plains, plain regions. And then if we go higher, if we go up to 80 meters, it's stronger yet, and still strongest in the Great Plains and offshore. Why is it strongest in the plains and the higher you go in the atmosphere and offshore? Where in the yeah, no obstructions.
No obstruction.
Yeah, so you think about a stream or even like a irrigation ditch, the water's flowing fastest right in the middle because it's not feeling the boundaries of the stream. There's no friction occurring with the walls of the river or the stream. So the same is the case with wind. When there's not as many trees as is the case in the plains, not any hills or mountains, relatively flat, then the wind speeds are going to be much greater. Same with the water. You just have to go north of like Smith Road here in Whatcom County, and it gets a lot colder and a lot windier because there's far less obstructions from foothills and Mount Baker when you're out in that Nooksack River Delta. So yeah, wind has tremendous potential offshore and in the Great Plains here in the United States. And in 2010, we have installed about 200 gigawatts, theoretical potential of 870 terawatts. So that was that first plot I showed, tremendous amount of wind available, enough to run society several times over. And I think today the world has 650 gigawatts installed, last time I checked. And somebody can double check me on that number. I don't know where it came from, my head. Here's zooming in on the United States for 2020, 109, 110 gigawatts of installed capacity. So we've increased fivefold over the last 10 years in the United States. And Texas completely dominates. And again, it's due to they have very laissez-faire power markets. Anybody can be a power provider. You can build a wind turbine on your ranch and sell it to the grid. And so Texas has a tremendous amount of wind power, followed by some of these states that are in that very high wind generating region, Kansas City, Oklahoma, and then places like California, Washington, and Oregon. Looks like Iowa has a tremendous amount too. I have no idea what's going on down here. There's plenty of jokes to be made, but I'll just refrain. Global installed wind capacity, totally dominated by China. They've just built a crazy amount of wind in the last 15 years. Germany was the leader in 2006 with 20 gigawatts, and they've been slowly building out their wind up to 60 gigawatts. United States has been building wind very, very quickly. And so we're up to, like 105 gigawatts, 110 gigawatts. But China just needs more electricity for everything. As their economy has taken off tremendously in the last 20 years, they want more nukes, more wind, more coal, more solar. They just want electricity because that drives their economy. Charting out global wind power capacity, you can see that it's still on this exponential growth curve. And so there's going to be much more wind next year than there was last year. Maybe not as much next year because of coronavirus, but we're still early on the learning curve. It's going to get cheaper and cheaper, and more will be built out over time. Aaron wrote, where do European offshore turbines fit in? I'll get to that in a second. There's, locations in Europe with not a lot of land mass and high population density, and that land needs to be used for other things. And so places like the Netherlands, Norway, and the United Kingdom are building a lot of offshore wind for two reasons. That's where it's available, still close to population centers, and better wind resource without those boundary layer effects. Here's some math. So wind gets its energy from kinetic energy. Kinetic energy is 1/2 mass times velocity squared. It's the mass of the air particles, and the velocity is how fast they're moving. The amount of power you generate from wind goes as velocity cubed, and that's because you get the v squared from the kinetic energy of the air particles, and then how much of that wind you get depends on how quickly the wind is moving, how much wind passes through in a given time. So that's where that third velocity component comes in. You can capture more wind particles, more air particles with a larger cross-sectional area, larger wind turbine radius. And so bigger wind turbines generate more power. because you get more mass, you have more air particles traveling through it. And so the thing to take home from this slide, unless you take Tim's Energy 320 class, then you'll see this a lot more, is that windier wind makes more energy and bigger wind turbines capture more wind. So it's not too difficult to get. You also want the bigger wind turbines also benefit from being higher up in the atmosphere. So they're further away from the ground, less boundary layer effects. And so the power generated by blade diameter really increases. When you double the diameter, you get nearly 4 times the power. And so these really massive ones can be like 2.5 megawatts. This shows the evolution over time of building bigger and bigger wind turbines up to about 2003. So they were up to like 120 meter wind turbines in the early aughts, 4.5 megawatts. And now we have some really huge ones. I think there's a 10 megawatt one off of Norway. Wind power isn't a new technology. I mean, Iran, I guess it's Prussia, modern day Iran. Prussia was using wind turbines, windmills way back in, 1000 BC. And then, yeah, Western society's been using wind turbines that they learned from the Persians about for, the last 1500 years or so. But the very first electricity generating wind turbine was still like way back in 1888. So we had renewable wind energy making electricity. Actually, all the energy back in the first energy was all renewable. It was hydropower and wind power. We didn't start burning things and running generators till later. So this is one, I believe it was in Ohio, that generated, I think, a few kilowatts. I forget. Okay, I have it written right here, 12 kilowatts. See another question in the chat. Do you think that climate destabilization will make wind, solar power more or less viable in any significant way? I think it will certainly provide an impetus. I think that yes, I sure hope so. I think people will become more and more convinced to switch off of fossil fuels when we feel the economic impacts due to climate change more and more. So this turbine here, I'm not going to bother to count, but it has like 100 blades. Why when you drive out to like Eastern Washington or down in California, why do they only have 3 blades? Why is this one got 100 blades? They're stronger now. But if you think about it, the way these work, so it's basically an airplane wing, and it creates drag, and that causes lift to cause it to rotate it. Okay, Jared wrote, blades cost money. Greater efficiency for less, most energy per cost. There you go, Emma. That's the answer. So yes, you'll get more energy with more blades, but blades cost money. And the peak of that ratio of energy divided by cost happens at 3 blades. So that's it. You can get wind turbines of all sorts, all sizes. You can even have a domestic, a residential wind turbine. So this one generates 1 to 2 kilowatts. The wind right at your house isn't that great. And so that's why it makes more sense to use a solar panel. It'll be more productive for a unit cost. You can build these really big ones at 2 megawatts. This is enough to power, a city or 2,000 homes or so. Here's an absolutely massive one, 120 meter tower in Norway, 2.3 megawatt turbine. And then the biggest one is 162.5 meters tall, and it can power about 10 megawatts, which really is honestly 20,000 homes, not 2,000. This one's so big you can't tell how big it is. One of those type of optical illusion things. There's more advanced designs that are in the works that people are thinking about. Namely, you're trying to get really, really high in the atmosphere. because winds get crazy fast. I know that's not a technical term. Once you get 30,000, 40,000, 50,000 feet in the air, and so they would have to be tethered. Most of them would be metastable up there. They would just be held aloft by the winds at that height, or they'd be filled with something like helium or hydrogen so that they'd float. This is actually this idea is one of Jack Dorsey's like side gigs in Oakland. But I don't know. This seems a little scary to me because like if it leaked, I wouldn't want it to like Donnie Darko on my head or something. Whoa. That was creepy that I made that joke and then a painting just fell. Oh well.
Charles, that made me laugh so hard in the middle. Was so creepy.
That was so crazy.
Right after that joke.
All right, I will try to contain my psychic energy within my head. Moving on. Issues with wind. Biggest issue is it's intermittent, right? It depends on the weather. Do we need to call 911? No, everything is good except for that painting. It was fungi week, and it was a painting of some mushrooms, and I let my girls like draw them or something. Did not hang it up well. Everything's good. So we'll talk all about issues with renewable energy about a week from now. But the biggest one is that it depends on the weather. And so this plot shows 30 days of solar installation in gold, wind generation in blue, and power demand in red. And this is for Portland, Bonneville Power Administration. And you just see that like wind and solar are highly anti-correlated with power demand. And so figuring out how to get these to match up using flexible energy strategies or energy storage is the challenge over the next 10 years or so. Yeah, chanterelles are delicious. Okay. Another big issue with wind is we saw where the best wind is right here in the Great Plains, but everybody lives here, right? In the urban centers on the coasts. And so this is a map of population, and so getting that wind power out to where the power demand actually is a challenge. We have to build something like high voltage DC power lines. And right now, the high voltage power lines, again, don't exist where the wind is. They connect large urban centers and large interstate power grids. Incidentally, you notice that none of these big power networks go into Texas, despite being a large population center. That's because Texas has its own independent power grid. That's the timing of it, the frequency is offset from all of America's power grid. And so they are able to secede from the nation at any time without having to worry about their power grid. Other issues, NIMBY issues, not in my backyard, things like this, lower property values. They do break. This is happening less and less as we learn more to make better wind turbines, ones that can be controlled. Their spin rate can be controlled electromagnetically, or if the winds are too strong, you can just feather the wind turbines and curtail them, turn them perpendicular to the wind so they no longer harvest wind. This happens due to different resonance effects. You know, like maybe you weren't as crazy as a kid as I was, but like waiting for a bus when I was a kid, you can like shake the bus sign. And if you shake it just right, it creates a resonance effect and can really get going. I once broke a stop sign doing that when I was a kid and stopped being that crazy. But same thing can happen with these wind turbines. It's just a cool picture. Okay, so pros and cons: low pollution, non-consumptive, small footprint. Those are the pros. Cons are they're ugly, they're noisy. The people that own golf courses don't like them. And then this other one is bye-bye birdies and bats. So this is actually something that gets a lot of pushback from wildlife Federation Foundation, World Wildlife Foundation, Sierra Club, and others. But it is true they kill birds, but a lot of other things kill birds too. And I hate whataboutism arguments, but we really need to pay attention to this. If you really want to save the birds, you need to get rid of cats. And just transmission power lines are killing birds. Shooting birds apparently kills them. It's bad for birds. So that's another problem. And then if you just look at other power plants, like nuclear power plants or coal and gas fossil fuel power plants, they kill a tremendous amount of birds. And that's because of the stacks, right? You have this superheated steam and hot CO2 coming out of these stacks. If a bird flies over that, they're going to get cooked. The one counter argument to this whole graph is that wind turbines do kill raptors and birds of prey, which are keystone species in the ecological web. And so if you kill all the hawks, it's bad for ecosystems. But we're already seeing signs that birds of prey are evolving to not fly near wind turbines. Again, it's just evolutionary theory. When birds that for some reason are scared of wind turbines are more likely to reproduce. And so now we're having more and more birds that are scared of wind turbines. Okay, switching over to solar PV. That was just a crash course on wind. Now we're going to do a crash course on solar. Here is a global mean solar irradiance. So that's how much solar energy is reaching any place on the planet. Here we are in Bellingham, not too great, but we get long summers with a lot of sun. So it evens out sort of over the course of the year. This map was generated by 3Tier, by the way, which is a renewable energy information company down in Seattle. It'd be a great place to work after you graduate. So the best locations, there's two things that make good locations on this map. Two geological phenomena. One's obvious, one's less obvious. Any guesses?
What was the question again?
There are two geological properties that make solar irradiance higher. Near the equator, yeah, so that's the obvious one. And yet Devin got the second, elevation. So the best location is like the Atacama Desert in Peru and Chile, the high plains in Central America, Mexico, Sahara, Himalayas, and all of Saudi Arabia, basically. Zooming in just on the United States, the best location for us is Arizona and California, Nevada. And then one of the worst places besides Alaska is Bellingham, Washington. But that's okay. Still worth it. How do photovoltaic solar panels work? They convert visible sunlight directly into DC electricity. We already talked about the potential. There's 100 gigawatts installed worldwide in 2013. Now there's 584 gigawatts in 2019. So it's growing exponentially as well. Not as fast as wind, but it's catching up. And it's going to overtake wind in the next 10, 20 years, just because you can put solar anywhere. And it's getting so cheap. You can put it on roofs. You can do big commercial rooftops like warehouse centers. Utility scale has ground mounted that can tilt with the sun. There's a massive utility solar farm in Germany. Just huge potential everywhere for solar. Okay, I'm gonna get a little nerdy for a second. The way this thing works is it takes advantage of a quantum level effect, a quantum mechanical effect, and that's that light can be viewed as little packets of energy called photons. And a photon with just the right amount of energy can knock an electron that's in a material from one conduction band, one valence band to a conduction band. So it can change the electron orbital. And that energy of light has to match precisely the difference in energy between those orbitals within the atom. And that's why it's a quantum effect. It's quantized, that energy jump. And so we can take advantage of that quantized effect and try to trap an electron and force it to go through a circuit before it returns to that original orbital energy level. So typically when light hits surfaces all around my room, it may kick an electron up to a different orbital, but then that electron instantly falls back down and re-radiates that light. And so if we can trick that electron to go through a circuit, do some work for us, rather than just re-radiating the light, then we can make a solar panel. So solar panels are made out of materials called semiconductors. Semiconductors have a gap between their valence band, where the electrons usually are, and this conduction band, where different atoms of that material can share electrons. Metals, there's an overlap between that valence band and conduction band, and that's why metals are such excellent conductors. Each metal atom is happy to share its electrons with the other atoms around it. Insulators don't share at all, and that's why they don't conduct electricity. So you can take a semiconductor like silicon, and you can force the electrons to arrange themselves in certain ways, even more so by doping them with elements that are nearby that have either one less or one more electron in the valence band. And so boron has one less, it's trivalent, has one less electron, and so it will it'll cause a slightly positive charge in the silicon semiconductor if you replace one of those silicons with a boron. If you replace one with a phosphorus, which is pentavalent, has 5 electrons in the valence band, it'll have a slightly negative charge. That's why this N-type for negative, P-type for positive. If this is way too crazy for you, don't worry. I've just given a quick overview so you have an idea of why this works. So in these P-type positively doped silicon semiconductors, this has a slight positive charge. The N-type has a slight negative charge, and this slight negative charge causes electrons to be attracted in this direction and holes or anti-electrons to be attracted in this other direction. And this creates an electric field. So what's happening now? Now you have this slightly positive region with a negative region because these electrons were attracted to that positive region and collect over here. The electrons that moved now left holes, and so this is slightly positive charge. And so this creates a slight electric field between these two layers in the semiconductor. So now when a photon comes in and hits an electron here and kicks it, if it kicks it enough that it goes into this other layer, it's not going to fall back down and re-emit that light as a photon, because it's going to travel this way and then see all these negative charges, and like repel, opposites attract. And so the electron will be like, there's too many electrons here, I don't want to go this way. And so it's forced to go a different direction. If you connect these two layers with a wire, then the electron will go through that wire and then go back to the P-type where it originally came from. And so then if you put a battery or a light bulb within that circuit, then now you have power, you have solar power. And so that's shown here. Here's the photon coming in, hits an electron in the P-type layer, it kicks it up somewhere to this region. It's more attracted to go in this direction because it doesn't want to see all these negative charges. And then it's captured by, in this picture, a wire to run a circuit. So here in this solar cell, you have a P-type semiconductor sandwiched with an N-type semiconductor. Light comes in, kicks an electron up. It doesn't want to fall back to the P-type because it sees this wall of negative charges. It's then collected on these current collectors, which is just a copper mesh of wire. And then the electron is returned to the P-type by going through some circuit. So that's basically how it works. Easy peasy, right? Just build one.
Wait, so like the extra energy that would have been, or like when the photon would have got re-emitted, it would have it would have lost energy, but within this system it just keeps it and like retains it, and that's how it like kind of siphons off energy from the sun.
Yeah, so the photon comes, kicks an electron to a higher energy state. Normally that electron would just relax back to its original energy state and re-emit a photon of the same kind, or possibly more photons of a lower energy value in the infrared band. But because it can't fall back down because of that electric field that's now been created by the N-type P-type junction, it's stuck in the N layer. And if you, eventually it will re-emit if you just didn't have a wire connected to it.
Yeah.
But that wire makes it attracted. It gives it an easy path for it to return to its original P-type semiconductor. And because that electron is flowing, it has a current and it has a voltage, and so it has power. Power is voltage times current, and you can power devices with it. And yeah, the energy from the light, rather than being re-emitted as light again, is converted into electricity.
Okay, thanks. That makes sense.
And yeah, so there's many different ways you can dope the semiconductors. You can use different semiconductors with different dopants and create different PN junctions, different solar panels that react to different frequencies of light, different energy levels of light. And so with different types of solar panels, you can capture more or less energy from the sun. You can have multi-layered solar panels with so-called double junction or triple junction that respond to different frequencies of light from the sun to capture even more energy from the sun. Much more expensive, so it's used for like military and space applications, but the technology exists. What you find on my roof or all over Bellingham would be these multi-crystalline silicon. It's the cheapest type of solar panel, and it's up to like 18-20% efficient at capturing solar energy and turning it into electricity. So it works great. You can use these different organic or thin film solar panels that have slightly different. Well, this one has indium and gallium as the semiconductor, and so it's flexible. And so this is what you find at like REI. You can put on backpacks or different things like that. A lot of different ideas here. Not as efficient, but they are low cost and much lighter. So different horses for courses, right? You can also do concentrated photovoltaic, and that's where you have all the sunlight collected on a mirror that then points all the light to a tower, a crystal usually, that then superheats salt or water that then can drive a turbine and make more conventional electricity that way with a Rankine cycle. And that allows you to, in a sense, store solar energy, because you can heat up a working fluid like salt or water or glycol and continue to run your power plant in the night when the sun's no longer shining. But right now, crystalline silicon, multi-crystalline silicon is so cheap that it's just totally dominating these other forms of solar generation. Here's a chart showing the best in class of solar panels. Efficiency is on the y-axis here. The stuff on my roof would be this multi-crystalline, so these open squares, so this kind of stuff. So it's peaking out at about like 20% efficiency. Stephen wrote, how efficient are mirror solar arrays compared to standard solar panels? I don't know. Good question. I don't know. So then to get past this 20%, you have to start doing more junctions. And so these double junction, triple, quad junction cells that can take advantage of more the spectrum of light coming from the sun. And so the best in class is like 44% efficient, and these are these triple junction cells. And these are all just the places that they've been created, and this is over time. And so, yeah, it's still early in the solar game, and it's only going to get better. Some environmental concerns with solar panels are toxins and glues, carcinogenic compounds that are required for their formation, and then breaking wildlife corridors. So if you put a massive solar panel farm in Arizona, you may disrupt migrations for turtles and things like that. Concentrated solar power towers also cook birds, and unfortunately some birds are attracted to them because it's this big shiny light collector at the top of the tower. But in generally, not much environmental harm from solar panels at all. All right, that was a ton of information, nothing on a test. I just wanted to give you an overview of how wind and solar works, how much is available, and what the future looks like for them. And we'll talk about the challenges next Monday. No class Wednesday. Dr. Joel Swisher is talking Friday. Please attend. And I'll hang out for about 10 minutes.
Thank you.
Thank you.
Mhm.
Thank you.
Thank you.
Quick question, Charlie. What can you give me like an overview or like because looking at back home, in the future, my family would like to put solar panels on our roof. And I'm curious we live near the base of Mount Rainier, so I mean similar to here.
Yeah.
So what's the cost benefits? What's the drawbacks? You have them and they're worth it for you. So is it about the same then?
Yeah. So my panels were 5 kilowatts, which used to be enough for my household, but now that I have a plug-in hybrid electric car and electric water heaters, I need like twice as much again. But so that 5 kilowatts cost $15,000 upfront. But right away, or a couple months later, I got a federal tax rebate for a third of that cost. So I got $5,000 back. And so it cost me about $10,000. I make $500 worth of electricity a year with them. So it will pay for itself in a long time, like 20 years. So it's not the smartest direct financial investment. That being said, the price of energy is thought to increase over time. It has, so it'll pay back more and more each passing year. And then depending on your housing market, the estimate for my house is that it added $9,000 of value. So if that's actually true, I only paid $1,000, and so then it will pay for itself in two years, and then it'll just make money for me. So I think it's a good. Yeah, Tony might have better advice. He has solar panels too on his house.
Just look at the Google Solar Roof to get an idea of what you can harvest. Once you know what you can harvest, then you can figure out the dollar equation on the solar roof thing is not terribly accurate, but the solar harvest is.
Yeah, so type in your address to like Google solar roof, and then see what it looks like.
Okay.
Yeah.
Sweet, thank you.
But it's fun, and it will save you energy and money too, because as soon as your parents start generating their own electricity, they'll go around their house and find all their inefficiencies, because it'll be exciting to try to maximize the return, right? And so it'll cause behavior changes that will save even more money.
Perfect. Okay. Cool. Thank you.
Yeah. Thanks for your interest.
Yeah, only one person has to turn in the outline in each group, right?
Yeah. Yeah. Just one podcast outline per group.
Okay, thank you, great.
Yeah.
Charles?
Yeah.
I just wanted to confirm, when's the podcast due?
The weekend after Thanksgiving. So just before the very last week of class. We will be listening to each other's podcasts that last week of class. So need them in by then. I mean, absolute would be like Thursday night before the very last class, but that's going to piss me off because then I have to assemble it and edit it right before class.
Okay.
Yep. All right. See ya, everybody. Any more questions? No. All right. Have a good one.
See you.